Hey everybody, Corey and Victoria here. We are the Professors DuBois, and we're going to bring back the electron configuration, but this time we're going to apply this to ions, and we're going to introduce a new vocab word, which is isoelectronic.
So the first one we're going to start with are anions, and anions, of course, are negative ions, a negative ion, right? So these are species that have gained extra electrons to become negative, and these are the easiest ones because they just fill as expected. So if you had extra electrons, you'd fill them as you normally would in your normal fill order. So let's give you an example here. Nitrogen has 7 electrons. So when you write an electron configuration for an ion, you want to write the electron configuration of the neutral atom first, and then either add or subtract electrons. So in the case of the anions, we are adding extra electrons. So for nitrogen, we're just showing you the orbital box for an example here on the left, and then on the right we have the complete SPDF notation. And we have 3 orbitals that are half filled, and lo and behold, nitrogen will gain 3 electrons to pair up all of those orbitals. So pair up the unpaired electrons to be completely filled. And what we end up with is an electron configuration that's the same as neon, which is a noble gas, and that is a lower energy state, and it's quite happy. So we just fill them as normal, so we end up with 1s2, 2s2, 2p6.
Now, cations are a little more tricky, but not bad. So the general rule is we remove the electron, because cations, okay, I should back up. Cations are positive ions. So positive ions are formed by losing electrons. So the general rule is that the electrons that are removed or lost are the ones with the highest N. Or, so this is the energy level, principal energy level, or the highest L if there's more than one subshell with the same N. So if we had, like in this example, we have the 2s2 and the 2p1, that 2p electron will be removed first.
So here's an example of removing from the highest N first. So of course we start with our neutral atom of, in this case, magnesium. And we can write it as the complete SPDF, see a little review here, or our noble gas configuration. And magnesium is going to lose 2 electrons. It makes an Mg plus 2, and it removes them from the highest N. So we have our highest N is 3, so it takes away those 2 electrons, and look at that. We are a noble gas again. And that is why magnesium will lose 2 electrons instead of 1.
Well, we're not really a noble gas, but we have an electron configuration that is the same as the noble gas. It's still magnesium ion.
Right. Thank you for that.
So this is where it gets a little bit tricky. So we have an electron configuration. We've got the 4d10 orbital, the 5s2, the 5p2. And if we're going to form the 2 plus ion, we're going to lose 2 electrons, and we have the 2 spots where the 5, the n equals 5. So we look to L. Remember, L is 0 for S, 1 for P, 2 for D, and 3 for F. So our highest L value here is the P. We're going to remove those 2 electrons first. So the ion formed is noble gas configuration shown with the krypton, 4d10, 5s2.
And what's interesting is tin also will make a tin plus 4, which means that it also loses those other 5 n equals 5 electrons.
And I think what's interesting and probably worth mentioning is this instance we did not come up with a noble gas electron configuration. So
right.
you don't always end up with a noble gas configuration.
Ions of transition metals. Okay, so these are the metals that are in the center part of the periodic table, and we do lose them from the highest N first and then the highest L, just like any other cation. And what we want to just kind of mention is that if you write your electron configuration in fill order, which is what you would normally do, if you rearrange that so that you have the highest N's last, and the highest N's and the highest P's of those N's last, like this, then what you can do when you make your cation is just remove electrons from that the outermost N. So it's very obvious to know which electrons to remove. So cobalt is polyvalent. It can be a cobalt +2 or a cobalt +3. So the cobalt +2 ion has lost the 4s2 electrons, and then the next one you would just have to go to the next highest end, so it would take from the 3d for that third electron. And the fact that many of these transition metals form +2 ions is explained by this, because all of our transition metals have these outermost s electrons. So it can lose those s electrons the easiest and often will then stop and become just the +2 ion.
So remember we had some exceptions when we were doing electron configuration. Specifically, we talked about chromium and copper. And one of the things, just kind of a watch out, is if you're working with chromium, the neutral chromium, and you're going to form an ion, you want to write the electron configuration as we would as an exception, and then remove electrons starting with the highest n. What we don't want to do is create an ion and then start promoting electrons. This doesn't happen. So if there's an exception, if we're looking at chromium or copper, we can write the neutral the way we should as an exception, remove electrons from the highest n. No other promotions or anything strange here.
Okay, so here's just another example here of chromium. So we have our chromium exception. We write our neutral atom first, our electron configuration, and this is in the noble gas configuration with the SPDF after. And when we make a chromium +3, for example, ion, we need to remove three electrons. So we go from the highest end first, so that electron gets removed first, and then we have to remove 2 from the 3d, and what we end up with is the argon 3d3.
And notice too, we rearranged the order for this. We put the 3d before the 4s, and the fill order the 4s would come first. It just helps to do the cations, I think.
Yeah. Isoelectronic, this is a new term, and isoelectronic, it means that something has the same electron configuration as something else. So species that are isoelectronic to each other have the same electron configuration. Well, what does that mean? It means they have the same number of electrons. So many ions that we've noticed today will either lose or gain electrons to become isoelectronic with the nearest noble gas. That's a very low energy state. That's a very, quote, happy state for the atoms, and they will lose or gain to become the same isoelectronic with the nearest noble gas. So here's a couple examples. We have the fluoride, the fluorine will turn into fluoride by gaining an electron and becoming the same as neon. Magnesium has 2 extra electrons. Beyond neon has 12 electrons, and it loses those 2 outer electrons to also be isoelectronic with neon.
So sometimes with these isoelectronic species, they'll ask you about the size comparison, like, which is the biggest? And we really want to go back to that effective nuclear charge, which is essentially based on the number of protons in the nucleus, because they're all going to have the same number of electrons if they're isoelectronic. So when we get isoelectronic species, we're going to go to the number of protons. The more protons, the smaller that species is going to be. That stronger effective nuclear charge is going to have a stronger pull on those outer electrons. Now, if we're just looking at the same atom and we're going to compare the atom to the ion, let's go with fluorine and the fluoride ion. Well, the fluoride ion gained an electron. This will be bigger. So if we add electrons, we're going to be larger than the atom. Likewise, with the cations that lose electrons, they become smaller when they form the ion. So if I was going to compare calcium to the calcium ion, the calcium 2+, I would say that the calcium atom is larger than the calcium ion.
So here's some practice. Pause the video and give these a try. There's quite a few, so give yourself some time and restart when you're ready. Here's your answers.
So I noticed for number 3, if we went back up and looked at this number 3 question, it says, what cation corresponds to the following electron configuration? Well, could it have been, we have the answer as the cobalt 2+, but could it have been, and let's see, would it be a nickel?
Nickel makes a 2+ as well, so that one wouldn't make sense. And iron makes a +3. Does that work?
We have a 3D, we have 3D7 here.
3D7.
So 1, 2, 3, 4, 5, 6 on the iron. So it'd have to be the nickel. I was just wondering if we could have...
Glad you started this.
I was just wondering if something could have lost 3 electrons. Maybe we lost one from the 3D as well. So that was a little bit confusing.
It could have been an iron +3, I think, as well. Iron +3 would have lost the 2 and then one of the Ds.
1, 2, 3, 4, 5, 6 though for iron, starting out with 6.
No, no, wouldn't work. Would have had to have been nickel, and nickel doesn't make that. So
there you have it.
There you go. Thanks so much for joining us. We appreciate you tuning in, and join us for the next installment of Gen Chem 1. Thanks for joining us.